Today, we will talk about the Electronic Flight Instrument System, which is usually abbreviated as EFIS. The EFIS is an integrated system of digital screens through which flight and navigation instrument information is displayed electronically. However, since each manufacturer designs its own EFIS system, there are several variants among the different models, so it is important to be familiar with the particular model to be operated. Now, we must also say that the introduction of the EFIS represented a drastic change in modern cockpit designs and their operating philosophies. For example, in the image on the left, we can see the cockpit of a Boeing 727 designed in the 1970s, when EFIS systems did not yet exist. While in the image on the right, we can see the cockpit of a Boeing 787 Dreamliner from 2015, where we can clearly see the implementation of the EFIS in almost all instruments. Now, this change did not happen abruptly from one day to the next, but occurred gradually. For example, in the first EFIS systems, the first instruments that changed their presentation from analog to digital were the attitude indicator and the horizontal situation indicator. These analog instruments were replaced by digital displays called Electronic Attitude Director Indicator and Electronic Horizontal Situation Indicator respectively. Here we can see an example of the implementation of these first EFIS systems in a Beechcraft King Air. As we can see, both the attitude indicator and the HSI were replaced by digital displays, while the rest of the instruments are analog. Another example can be seen here with a Cessna 172, where again, the attitude indicator and heading indicator were replaced by digital displays. Now, so far we have seen the partial implementation of the EFIS system in the flight instruments. However, when we talk about a complete EFIS system, we use the term glass cockpit. This term refers to cockpit designs composed entirely of digital displays, as we can see in these images. On the left we have the Garmin G1000 system installed on a Cessna 172, while on the right side we have the ProLine 21 system installed on a Beechcraft King Air. Now, the components of a complete EFIS system are the displays that show the information to the crew, the control panel by means of which the system can be controlled, and one or more symbol generators. Let's now take a closer look at each of these components, starting with the displays. These units present the processed information from the relevant instruments and systems to the pilots. We have already seen some of the displays used in partial implementations of the EFIS. However, in complete EFIS systems, other displays are used, which are known as PFD and MFD. Let's see a brief description of each of these displays and the information they provide, starting with the Electronic Attitude Director Indicator. It consists of an electronic display of the attitude indicator and the flight director. However, in some cases it may include some additional data, such as the ILS deviation scales, a flight mode annunciator, the radio altimeter, and a relative speed scale. And although the design and presentation may vary slightly between models, this type of instrument does not include altitude, vertical speed, or indicated airspeed information. With this being said, let's now look at the Electronic Horizontal Situation Indicator. As its name suggests, it consists of an electronic presentation of the HSI. However, it may include some additional functionalities such as ground speed, DME, RMI, and even a graphical representation of the flight plan. However, this type of instrument does not usually include advanced features such as weather radar or terrain. Now, on complete EFIS systems, we have the PFD, which stands for Primary Flight Display. It consists of an electronic display that includes several instruments such as the attitude indicator, the altimeter, the airspeed indicator, the vertical speed indicator, the heading indicator, and the slip and skid indicator. And in addition to this, it may include some additional data such as the ILS deviation scales, a flight mode annunciator, a radio altimeter, and the frequencies for navigation and communication. So as we can see, this display condenses the 6 basic flight instruments into a single presentation, which results pretty convenient for the pilots, and that is why it is called Primary Flight Display. Finally, we have the MFD, which stands for Multifunction Display. However, depending on the manufacturer, it may also be called Navigation Display, abbreviated as ND. It consists of an electronic presentation of the Horizontal Situation Indicator that includes advanced features and functionalities related to navigation, such as true airspeed and ground speed indication, wind direction and speed, DME, RMI, a graphical representation of the flight plan, weather radar, and terrain. Some of these displays even include information related to the engines and other aircraft systems, as we can see in this example with the Garmin G1000 system. This is common on smaller aircraft that do not have displays dedicated exclusively to engine and systems monitoring. Now, in larger and more complex aircraft, we can find displays such as the ECAM or the ICAS, which are dedicated displays for monitoring and indicating engine parameters and other aircraft systems. Now, the technology used in the displays of the first FE systems consisted of cathode ray tubes. However, today most FE systems are equipped with liquid crystal displays, which are much more efficient and reliable. Now, another important change caused by the introduction of the FE system is the way in which information is presented to pilots. Since the great flexibility offered by digital instruments in relation to analog instruments has made it possible to redesign the way in which the information of each instrument is presented. This way, digital instruments are easier to read, they present less ambiguity, the information is more accurate, and they have intuitive, simple and clean designs. With this being said, let's now look at the control panel. This unit allows the crew to control the information displayed on the FE's displays, as well as to control the brightness. However, as previously mentioned, the design and functionalities of this control panel varies depending on the manufacturer and model, so it is important to be familiar with the control panel to be operated. Now, let's see the last component of the system, which is the symbol generator, abbreviated as SG. This unit acts as the interface between the aircraft systems, the FE's control panel, and the displays. In other words, it processes the data received from the systems, and taking into account the settings selected in the control panel, it generates the image to be displayed on the screens. This symbol generator may be known by other names, such as display management computer, display processing computer, display electronics unit, among others. Let's see an example of how this unit works. Initially, the symbol generator receives the information from the aircraft systems and sensors, which provide all the information that must be displayed to the flight crew. Then, the unit takes into account the settings selected in the control panel to generate the image to be displayed in each screen. Now, regarding the system layout, light and simple aircraft usually have only one symbol generator, since typically, these systems include only one PFD and one MFD. However, larger and more complex aircraft usually have up to 3 symbol generators. In this case, under normal conditions, the captain's sensors will provide information to the symbol generator number 1, which in turn will generate the images for the captain's displays. On the other hand, the first officer's sensors will provide information to the symbol generator number 2, which in turn will generate the images for the first officer's displays. In addition to this, both the pilot and co-pilot sensors will send information to the symbol generator number 3, which will be the backup unit. This way, this backup symbol generator will be able to generate the images for any of the displays. With this in mind, if one of the units fail, the backup symbol generator will be used to provide information to the affected displays. In this example, the symbol generator number 1 failed, so the unit number 3 is now feeding the captain's displays. In some cases, the pilot can even manually select the symbol generator to be used for a certain display. However, the operation of this system varies depending on the manufacturer and model. So far we have seen what happens in case of a symbol generator failure. Let's now see what happens if one of the displays fail. In this case, the pilot can select to have the information displayed on another screen. However, once again, the operation of this system varies depending on the manufacturer and model. Now, the symbol generators not only process the information, but also monitor the system. Each symbol generator is responsible for performing the following monitoring processes: data validation, which verifies that the information coming from the systems and sensors is valid; data comparison, which compares the data processed by the unit with that of the other symbol generators; and display monitoring, which monitors the integrity and performance of each display. By now, you might be wondering, what happens in case of a total system failure? Well, most aircraft have a backup instrument system completely independent of the FEs. This standby instruments can be either analog, as we can see in this example, or they can be digital as we can see in this other image. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.